Welcome to our read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 6.1.6. We're going to practice finding the Smith normal form. All right. So we kind of have this type of idea. If we get a 1 in this upper corner, we can use that 1 and play it against things below it and to the side of it and clear it out. So you have 1s, 0s, and 0s. Then you have the rest of matrix and you repeat the process iteratively. You get a 1 up here and then you go down and over. You use that to play against things to clear out, clear out. Okay, so let's try to find, and that's a basic procedure. We don't have to do that, but we could. Another way of doing this is we could do all the row operations. And then after doing all the row operations, do all the column operations. Because arrows going this way are column operations, and arrows going down this way would be row. Okay, so let's find the Smith normal form of this matrix. All right, R1 and R2 stand for rows. So row 1, row 2, and these are the names of the columns. Okay, so here's kind of a notation for operations. What if we want to replace row 1 by half of row 1? We can just write this out. Okay, so we do that. Then in here, we're going to replace row 2 by row 2 plus our row 1. So row 2 becomes itself plus a multiple of another row, just that itself. And you end up getting this right here. So kind of literally what we're doing is we're taking row, and let's write this out. So quite literally what we're doing is we're taking this one right here and we're playing it against that guy. We're taking 1 times this row and then flopping it down right here. So this one airlifts into the air, multiply it by something just positive 1, and then drop it right here and see what happens. So when you drop it on these numbers, 1 plus -1 is just 0, 1 plus 2 is 3, and 0 plus 2 is 2. So we were successful there. Now, right here, what are we going to do? Now, we're using this procedure that we have this 1 here and then we cleared out. Now let's clear out this way. So we're going to get some column operations going on here. So for column operations, we simply take this column 1, 0. Okay, we take this column 1, 0. And we airlift it, multiply it when it's in the air, airlift it, we multiply it by -1. So -1 and 0, that's kind of what it is when we airlift it. And then we add it, drop it right here. And the effect is to make a 0 right there. So we cleared that out, made that 0 right there. So, and then what do? We do another column operation. We can take this, let's see, we're right here, okay. So right here, we could first, let's just, since we've established this 1 with zeros that way and that way, let's go to the next part of the matrix. Let's make a 1 right here, which we can do by doing a column operation. Divide this column by 3 to make a 1. Now, let's do some column operations to take this way. Okay, so we're going to take this column and multiply it by -2. So we airlift it. And when it's in the air, multiply it by -2. So we get 0 and -2. And then we plop it, drop it right here, this column, and it becomes 0, 0. And then we were successful at finding the Smith normal form for our beginning matrix. Okay. All right. Okay, so what do we notice? This matrix right here, we get the Smith normal form. So that tells us that the kernel of this matrix, the dimension of the preimage of 0 of this matrix, or thought of as a map, is going to be, how many 0 columns do we have? We have 1 0 column, so the dimension of the kernel is 1. Dimension of the range, or the full image, is 2. Okay, so in a similar way, we can find these row and column operations on this matrix. Okay, so looks like for starters, Okay, we can just divide each column by different things and end up getting something like this. Then we're going to clear, we see this one, we clear out what's below it. We like take this guy right here, this row right here where the 1 is at the top, you airlift that row, multiply it by -1 and plop it down on this part right here. So -1 and -1 is airlifted, and then you plop it down here and you get zeros. All right, we're almost done. Now we can like take this guy, multiply it by negative and in the air, and then plop it right here. So we end up getting this as our Smith normal form. Notice that the current dimension of the kernel is 0. The dimension of the range is 2. Dimension of the codomain is 3. That's because there's 3 rows. Okay, so, but the dimension of the kernel plus the dimension of the range is equal to the dimension of the domain. Okay, even though the codomain could be bigger, but that's fine. Okay. So, and we can do a similar thing here. Here's another example. Find the Smith normal form using row and column operations. Here we end up getting something like this. Dimension of the kernel is 2, dimension of the range is 2. Okay, and we'll end that. Let's see what's left here. Just kind of look at the rest here before we end. So there's another couple little subsections which are, I would say, more optional, but they can kind of give you a few insights depending on what exercises you want to be looking at in the section, because they actually could help with some of them. So why fields? Like, why are we using fields, right? Couldn't we do something like with Z modules? And the answer is we can. The only difference is that we can't always get a nice Smith normal form with 1s because that involves dividing sometimes. However, if we just did the best we could and didn't worry about necessarily getting 1s, what we can at least do, at least for Z modules, free Z modules, is we can at least get a diagonal. That's one nice thing about free Z modules. And there's actually information that we can glean from that. This is by working through that. So we can't find a Smith normal form with 1s, but we can just do the best we can, and it still gives us some valuable information. Okay, all right. And note on freeness, there are some technicalities with the Smith normal form ring which we won't really get into necessarily with which depend on divisibility, but at least but for our sakes, we're it's good enough. It's going to be it's going to be close to the Smith normal form on the standard one, but for our purposes, we'll just let it go. Right here for this last section, this basically runs through a proof that if you have a field and you have f, and you take any f module, it's actually going to have dimension and be free. And so this is a little proof. It actually uses, at least for the infinite case, it uses Zorn's lemma, which is something discussed in one of the exercises in a previous chapter. But but that basically concludes this section. Thanks for watching.